Hi, my name is Danilo from Universidade Estadual Paulista, Júlio de Mesquita Filho, Unesp, in Presidente, Prudente. I'm from the Departamento of Matemática e Computação, here in Faculdade de Ciências e Tecnologias. And I'm going to present this paper from BRACIS, which is a visual approach to support analysis of optimum-path forest classifier. The OPF classifier is a graph-based classifier. The first step of this OPF framework is to compute the distance between among all instances. In this case, we are using a complete graph to compute the distance of all instances. Each node here represents an instance, and the edge is the relation of each instance, computed by means a distance measure. The second step is to compute a minimum spanning tree. Here is an example from the complete graph using the weight, the distance as weight. We compute here the minimum spanning tree. Now we have to identify some prototypes. In this case, the prototypes are that instance that represent a transition between classes in the spanning tree. So we start a conquer process in which each instance we compute an optimum path for each instance to a prototype. So from the conquer process, we have optimum path trees related to each prototype. When in the classification step, when we have a new sample, an unlabeled sample, we compute again the distance from this new sample to all samples of the training set. Here, the edges represent the distance from this new sample to all other samples. Now, we have to apply again the conquer process to establish a relation from this new sample to a prototype. This relation is based on an optimum path from this new sample to a prototype. Here's the example of the optimum path from the sample to that blue prototype. And now we establish as the label of this class the label of the prototype. Here's the example of a prediction. This new sample is now predicted as the blue class because this instance has an optimum path to a blue prototype. So usually when analyzing the results of OPF classifier or any other classifier, we can employ some measures like accuracy, F1 score, precision, area under curve, rock analysis, and others. But all of these measures only present a summary of the performance of the classifier, in this case the performance of OPF. And it's difficult to understand the behavior of all the process of the OPF, the training process, the conquer, the optimum trees, and other steps. So, how some issues, some questions remains after analyzing the classifier using that measures. For instance, how is the boundary between groups of distinct classes? Are the prototypes adequate to represent boundaries? Are the optimum path trees sufficient to represent those groups? Why were some instances misclassified? These questions we are going to try to answer using our visual approach. So the main goal of this work is to aid the analysis of OPF and answer all of those questions, showing all steps in a graphical representation of the feature space. For that, we use the similarity representations in b-dimensional space. That is, a high-dimensional space is mapped to a 2D space by means of dimensionality reduction techniques. Here's an example. Given a high-dimensional space, we can compute into the similarities of the similarity of the high-dimensional space are mapped to a b-dimensional space by means of a dimensional projection. That is a dimensionality reduction technique. Here's an example of a document collection, document data set from articles that we get from 3 areas of artificial intelligence. We can note that the dimensionality reduction techniques can map the similarities in the b-dimensional space, so we can analyze the clusters, the relationship of the instance from the high-dimensional space in the b-dimensional space. Here in this case, when two instances, in this case two documents, are close in the b-dimensional space, it means that they are very similar in the high-dimensional space. So with this approach, we can map a dataset and compute each step of the OPF. For instance, here we are showing initially this is the iris dataset, a sample of the iris dataset, in this case a sample that represented the test part of the OPF. Here at the left we have the dimensionality reduction of iris dataset. We can note the groups. We can note a boundary between two groups, for instance the green and blue groups. A group apart, that is the red. So with the dimensionality reduction we can note and understand the feature space, the similarities of the feature space. Here we are mapping the MST, the minimum spanning tree computed by means of the edges, and also we are mapping the prototypes as the X, the cross representation. We can note the relationship of the prototype between distinct classes, as we showed in previous slides. At the center, we have the optimum-path trees. Here we can note how OPF computed a very concise group. The red is represented by one unique tree. The green and blue, we can see that were split in distinct trees, especially in the boundary of green and blue groups. We can see a lot of prototypes to establish a relationship among the distinct groups between the boundary, because it's an important point that the boundary have to be well defined so that the classifier can make good predictions. So in the last figure at the right, we can see here overlapped over the test dataset over the training dataset. I'm sorry. We are showing here the training dataset at the left, at the middle, and here at the right we are showing the training dataset and the test dataset in transparent way. The opaque is the training dataset, and the transparency was used to show overlapping of the test dataset. And we can see here the classification step. We can note that in the red group, all instances were predicted as red class. It's right. We can note here some misclassification in the blue group, and we are going to show in details in the next. Here a detailed inspection of this process, the MS3 and prototypes, the optimum-path trees, and here the prediction. As I'm told you, the triangles here represent the wrong prediction. We can note a blue triangle here at below the figure that is connected to the green tree. That's a misclassification. And we can note the correct prediction of almost all instances that were connected to the right tree. Here is the example I told you. The blue triangle indicates a wrong prediction, that is, the class is blue and was connected to the green of other class, in this case the green class. Here's the detail of this wrong connection. Here I'm showing you right predictions, the correct predictions. The instances were connected to the right tree, blue instance to blue trees, and green instance to a green tree, in this case only to the prototype. Some experiments we're going to show the usefulness of our approach. Here we use the datasets available in libopf, a dataset with 2 classes, and another dataset with 5 classes, and MPEG-7 dataset. For dimensionality reduction, use the classical multidimensional scaling to preserve as most as possible the high dimensional space, and we use the Euclidean distance for the dimensionality reduction, because we also use the Euclidean distance to compute the distance to OPF classifier. Here we are using the MS3, the data tree dataset from libopf. We can note here when we compute the MST that one prototype was enough to represent the boundary from groups that are too distinct or that are too far in the high dimensional space, here represented in the b-dimensional space. And when we have a boundary shared by distinct groups, we need more prototypes to represent this boundary, like the cyan and blue groups. Here a detailed inspection of the prediction. We are again plotting the opaque is the training dataset and the test dataset as with transparency, and we can note here a wrong prediction in the boundary. Usually the boundary is a delicate point in which we have to pay attention to establish good prototypes. Here the detail, we can see that 2 classes of cyan class, 2 instances of cyan class were incorrectly predicted as the blue class. They were connected to the blue prototype. Here we can see the wrong predictions, 3 wrong predictions of this dataset, and all of them in the boundary of the groups. So we could here try to establish a new choice of this prototype. Here we changed the prototype, manually changed the prototypes. That's an advantage of visual inspection. We could prepare our training data set to better represent the boundary. Here we are better representing the boundary with new prototypes. So after the manipulation, we could see that no wrong prediction occurs in the OPF. At the left, the automatic choose the automatic identification of the prototypes at the left, and we can see that the boundary was not well defined. And here, with this new manipulation, we can see that the boundaries was well defined by new prototypes. So we get 100% of correct classification. Here's an example in which we are going to show if the boundary is well defined and also the overall of the cluster is well defined, we don't need a lot of instances. Here we are going to show training sets with 70% and 5%, and we can note that at left is the 70% and at right the 5%. You can see that if the boundary is well defined, we can note this well defined boundary in both cases with well defined prototypes, and we also can note that at right, if the cluster is well defined by a tree covering all the cluster, it's enough to establish a good performance of the OPF. Here is the meaningful spanning tree. Here's the optimum-path trees computed, and here is the prediction. We can note that the accuracy is too similar. In the left case, we use a lot of instances, and in the right case, we used few instances. But the few instances was enough to perform similar to a training model that used a lot of instances. So we can show here that OPF don't need a lot of instances in the training dataset if the cluster is well defined and the boundary of the cluster is well defined also by prototypes. Here's a detailed inspection of the boundary. You can see here one incorrect prediction, the blue triangle. Here, four incorrect predictions that was in the boundary. We could also improve this boundary to reach a better performance. For instance, here, the impact of, we are going to show here another parameter of the OPF, that is the random selection. For instance, the random selection for choosing a training dataset can be a wrong choice because it can select instances that not represent well the boundary of between clusters. For instance, at left, that was a good random selection, and at right, a not so good random selection. You can see here on a few prototypes to define the boundary in the training dataset, and as a consequence, as a result of that, we get a worse performance of the training of the prediction of new samples. The accuracy was impacted. Here's another example in which we show that if the feature space is not enough to establish a good relation among the between instances, that is, if the feature space is weak or the features is not enough to establish cohesive clusters and to separate the clusters, we can see this result in the bidimensional space by the dimensionality reduction, and as a consequence of we don't have a boundary between clusters, that is, every instance is considered as a cluster. There's a lot of transition between classes, and almost all instances of the training dataset is considered as a prototype, and that it can impact the prediction of OPF, and we can see here a bad accuracy of this classification of MPEG-7. To conclude, we present here a visual approach in which we can note how the OPF classifier works. In our perspective, in our point of view, is an interesting approach to understand how OPF works, and also to teach and to users learn how OPF works. We can see here in practice with real datasets, with real feature space, how OPF works. We could show the instance similarities into the space, how the minimal spanning tree in practice, and how the prototypes can impact the OPF performance. We show the OPF trees and also the prediction process. Based on that, we show how to improve the choice of prototypes. We can impact the prototype identification, and with this manipulation supported by the bidimensional visualization, we can improve the training process by selecting new prototypes to better define the boundary of the clusters. We indicate how OPF can improve the prediction without increasing the training dataset. That is, if the cluster is well defined and the boundary is well defined, the OPF can get good performance in the classification. And also illustrate how the random computation of the training set can be a risk to the OPF performance. That is, the prototypes have to define the boundary of the clusters, and a representative instance have to cover all the clusters. To conclude, we think that this is an interesting approach to teach OPF. In future works, we'd like to choose or propose a new method to choose more adequate representative instance to the training datasets, an approach that cover the cluster and represent well the boundary. And also the visual approach could be better used as a guidance for choosing prototypes on the training process. And also to avoid overplotting the visual clutter, as we saw in the MPEG-7 and others huge datasets, and a hierarchical visualization approach could improve the exploration of large datasets. For example, only presenting details of the boundaries, prototypes, and representative instance. Here's my contact. If you want to collaborate with any kind of this project or other projects, we can contact me, send me an email.